Just as Michael mentioned, I'm a mission design engineer with AI Solutions. Worked on a number of low Earth orbit missions to libration point missions to deep space missions. And so one of the tools that I built my time here at AI Solutions is this two-level targeting tool that I built completely in FreeFlyer. So some of the motivation behind this work is that we all know that there's a lot of missions, particularly around the near the moon, and there's Sun Earth libration points that that are being launched or have been launched. One being ACE-1 in SOHO, which has gone to Sun Earth L1 point. The James Webb and the Roman Space Telescopes are going to be launching hopefully soon to a Sun Earth L2 point. And then, as Diane and Michael talked about just previously, the Gateway is going to be going to an Earth Moon L2 near rectilinear halo orbit. And similarly, the Artemis 1 mission is going to be going to a lunar distant retrograde orbit. Because a lot of these orbits are deal with sort of the balance of the gravity between the Earth and the Moon, or the Sun and the Earth, they're really sensitive, and they require sort of alternate strategies in order to obtain a longer-term reference trajectory in a higher fidelity ephemeris model. So instead of just picking a single point that has orbital elements associated with it and propagating it forward, then it'll stay sort of relatively in the same space. We have to come up with a different strategy in order to do that, to maintain the geometry that we want for, say, an NRHO or a halo orbit. So typically the way this is done is first looking in a lower fidelity model, say, for example, the circular restricted three-body problem, which is what I'm going to be showing today as my low fidelity model. And this model in particular only uses the gravity of the Earth and the Moon, and it assumes the Moon's in a circular orbit around the Earth. And then, however, our higher fidelity ephemeris model uses, there's a lot of other forces that are in there. We don't have a perfectly circular orbit of the moon around the Earth. We don't have a uniform gravity field. We have solar radiation pressure. We have the sun that can be included in there, and then other perturbing bodies, Jupiter, for example. So one way to sort of deal with this transition between a low fidelity and a higher fidelity model is using a targeting or differential correction scheme to transition between the two. So that begs the question of what is a differential corrections or targeting scheme within trajectory design. So some of you may have heard of differential corrections before, and FreeFlyer has one built in. However, there's a number of different types of differential correction schemes. But what basically they are is you're using linear relationships from perturbations from an initial state and looking at the final perturbations and using those to sort of build a continuous trajectory and achieving constraints that you want on your trajectory. So for example, we're going to be looking at position and velocity continuity, but you can also add in altitude constraints, delta V constraints, apse constraints, anything you can think of under the sun. As I mentioned, there's a few different types of targeting methods. One being a multiple shooting technique, which is a little bit simpler, but today we're going to talk about a two-level targeting. And this scheme, what this does, the reason why it's different than, say, a multiple shooter is it attempts to separately achieve position and velocity continuity through two different processes. So just visually how this works. So say we have a reference trajectory in our circular restricted three-body model, just shown here in blue. And this is relatively simple to get. And what we do is we take this trajectory and we discretize it into a set of nodes, or what we'll call patch points. And if we take those patch points and then propagate them in an ephemeris model, we'll notice, since our force model is different, that they're going to be discontinuous. We're going to have discontinuities in both position and velocity. So what we have here is we have at the end, and between these segments, we have position and velocity discontinuity. So what we want to do is correct them. So on our first process for this two-level targeter, what we're going to do is going to update our velocity components at each of these nodes or patch points to try to achieve position continuity. And what that looks like is here, but now it's clear that we don't have position continuity. We don't necessarily want to do delta V's every time we hit one of these nodes. So we run another process to update our position in order to achieve velocity continuity. And basically the way this works is we sort of bounce back between these two processes in order to get a fully continuous trajectory, while sort of maintaining the original geometry that we had for that we found in our low fidelity three-body model. So the first example that I'll show today is just using a simple L2 Earth Moon. I'm sorry, Earth Moon L1 halo orbit. Now this is unstable in the Earth Moon system. So if we were to take a single point on this orbit and just move it to ephemeris monopropagated, it would depart fairly quickly. And so the orbital period of this is about 12 days. So if we use 10 revolutions of this orbit and 4 patch points per revolution, this is going to be about 120-day propagation. So I will bring up my FreeFlyer script here. And so if we run this, I have a GUI here that has a number of different things in here. One being this particular patch point file option. So if we take the file take a file I've created here for the L1 halo orbit that has all the nodes in it, we can select our base epoch. We have tolerances on our targeter to which we consider a continuous trajectory when the nodes are converged to position of velocity continuity. Now, the reason we have a base epoch in here is our 3-body model doesn't consider a base epoch like a Julian date or anything. So but our ephemeris model does. So we have to select what that is. And so I'll just leave this as the default of 2024. We have other things in here. Attenuation factors. What they can do is limit the size of the update for each of the iterations. So that if you have a really sensitive trajectory and you want to sort of slowly try to correct it, because if you take too big of a step, you'll bounce out of the solution space and won't get the geometry that you want. And then there's some other options here for visualization. So what we'll do is we'll center the visualization around L1 since we have an L1 orbit, and I'll run this, and hopefully it'll run fairly quickly. And notice over here we have a few different, a little bit of information over here. So what this is trying to do is it's trying to achieve position continuity to less than a meter, and then velocity continuity to less than a millimeter per second. So after it's converged, it plots the orbit in the Earth Moon rotating frame, and we have an inertial frame down here. So I'll bring up the inertial frame first. Now we notice that this orbit is very much not conic. It is a little bit more difficult to work with, just compared to a conic orbit. So that's why we need these processes to do this. If you look at our rotating frame, we sort of maintain that geometry that we wanted to, but it's important to notice that we're not completely periodic. So if we were to take one of these states and propagate it, it would depart fairly quickly. So after just a few iterations over here, we've gotten our tolerance down to an acceptable level. And what this does afterwards is it pops out a FreeFlyer ephemeris file, which you can use for any sort of analysis afterwards to do look at lighting conditions or calm conditions and what have you. So going from a simplified 3-body model all the way up to ephemeris, it was just a few clicks. So that's can help a lot with dealing with these really sensitive trajectories in a higher fidelity model. And there's a few other plots here for altitude above the moon, and then looking at the position of velocity components as well. So go back to my presentation here. Additionally, I have a second trajectory that we'll look at. So this one's a little bit more complicated, and what this is a Sun-Earth L1 Lissajous orbit. So this is a quasi-periodic orbit in the Sun-Earth L1 circular restricted 3-body problem, and this trajectory resides on a torus in the 3-body model. I won't go into what a torus is, but effectively you can compute one of these in a 3-body model and get a dynamical structure in there. However, this is a complex trajectory just to start with and to compute just starting in an ephemeris model. So what we'll do is we'll take a little over 12.5-year propagation and use 100 patch points total to sort of try to stress this targeter to see how it does. So if we go back into our mission plan here, and we'll run this guy again and bring up our patch point file for the Lissajous orbit here. Oops. And then you can change our tolerances a little bit. So since this is in the Sun-Earth system, we're going to have to tighten our tolerances because these are all non-dimensional quantities here. So we'll set this, since this is an L1 orbit, we'll set the visualization L1, and then we will run this guy. So down here, we're looking at, a tolerance of about 15 meters, and then, about a little over millimeter per second for our velocity tolerance. Now, since this is a little bit longer, we have a lot more propagations here. So for every patch point, you have a propagation, and then you times that by the number of iterations. So every iteration you're running 100 integrations. So FreeFlyer is pretty good at handling this, especially considering the force model you're working with. So while this is running, I'll go and dig into the code here and show really the crux of what's going on. So what this particular mission plan relies on fairly heavily is both the matrix math and the state transition matrix in FreeFlyer. So particularly using the variational equations for the ephemeris model. Now, if anybody's anybody has had to code this up on their own, it is a tedious process to do all 36 elements of the state transition matrix and propagating them forward and validating it and everything. So FreeFlyer having that in there is really, really nice, since you can just call it and just propagate the equations of motion for both the STM and the state vector and just get it out fairly simply. And what that does is it gives you the variational relationships between your initial states and your final states, which is really the essence of any sort of targeting method. Additionally, the matrix math that is used here now to do each of these updates, we have we build these really large matrices, so on the order of tens of thousands of elements. And then we have to do an inverse of that every iteration. So having the matrix math capability in FreeFlyer really helps make this work fairly quickly. So I'm using an RK89 propagator in the background, so that keeps the accuracy of the trajectory pretty well. So if we take a look at this orbit finally, and I forgot to mention the gold points here are the patch points after it's been finally corrected. So we notice here this looks very similar to the trajectory we originally had, and it took a number of iterations here, but only took about a few minutes to run. And then again, this is output to a FreeFlyer ephemeris file, and you can do any kind of you can use that as your reference trajectory for any kind of analysis that you have to do going forward. So this is sort of the all that I have for today. We can take a look at the inertial frame here too as well. Now notice that this is again very much not a conic orbit. So using this two-level targeting method not only helps us transition these really sensitive trajectories to an ephemeris model, but also keeps it very close to, or attempts to keep it very close to what our original three-body trajectory was from our simplified model. So with that, I kind of flew through that, but if you guys have any questions, I'd be happy to answer them.
All right, thanks for that, Brian. We do have a couple of questions from the audience, and if you're in the audience, we do have time for a couple more, so go ahead and get those submitted in. First one is, in what set of coordinates is the STM usually computed, and can we have it in any reference frame that we have predefined?
So the STM is propagated, since the state vectors in FreeFlyer are propagated in the MJ2000 frame, inertial frame. That's what the STM is in as well. I don't believe that there's any functionality to do it in a different coordinate system. The FreeFlyer team may be able to answer that a little bit better, actually.
Great. FreeFlyer team says you're absolutely correct.
Great.
So, nice job. How did you make that really awesome FreeFlyer logo in the console?
I can't say I did that all myself. I took the FreeFlyer logo and passed it to one of these ASCII art converters and online, and that gave it to me out. So,
Gotcha.
Gotta have a little bit of fun with it.
How are you selecting your patch points from the reference trajectory?
So there's you could write an entire PhD dissertation on how to select patch points. I just sort of use I guess it's sort of a balance where you need to pick enough to where you're capturing dynamics so that this targeter that has these linear variations can correct to the geometry you want. But also you don't want too many because all of those little discontinuities that you're considering continuous are going to build up if you have a whole bunch of patch points along a trajectory. And again, the more patch points you have, the larger the problem you have to solve, and the larger matrices you have to invert. So it's sort of a balance between that. So I guess there's not really a good answer. It sort of takes a little bit of intuition and working with it to do it. But given that the ephemeris model is a lot more sensitive than say a three-body model, you typically need to use more when you're going to an ephemeris model.
Gotcha. Is there any freedom to add other level 2 constraints like apse line, altitude, flight path angle?
Yeah, absolutely. You can add. I have not built that functionality in yet. That's sort of like one of my next steps is to do that. But yes, absolutely. To build in, any kind of those constraints would be really helpful. So right now it's just getting position and velocity continuity right now.
Gotcha. How many iterations did it take for this example to converge?
Let's see here. So for so I guess to explain sort of the iterations here that are being shown, each of level 1 will run a series of iterations in order to converge to get position continuity, and then you'll run one level 2 iteration to attempt to achieve velocity continuity. So typically the way I would count this is the number of level 2 iterations. So 1, 2, 3, 4, 5, 6, 7. So it took seven level 2 iterations.
Gotcha.
And ideally, what you'll have is you'll have a your level 2 iterations will always decrease as you go down. So that's one of the sort of the benefits of using a 2-level targeter is that you're almost usually guaranteed to have level 2 drop as you're iterating each time for level 1.
Is it hard to write one mission plan that converges for a variety of different kinds of orbits?
I guess this one is sort of the way I wrote this is pretty general. So if you have any set of patch points, really it can be for any orbit or trajectory that you can pass them in, and the information from those patch points is really agnostic to any type of orbit that you want to work with. I guess the more difficult parts come if you have trajectories that pass really close to a primary, or where you're going to build up like a lot of nonlinearities. You either have to use a lot more patch points, or you'd have to modify it to sort of do some sort of forward and backward shooting. But right now mine's only set up to do forward shooting.
Gotcha. Let's see, is there a canonical reference for 2-level targeter in the literature?
Yeah, there are a couple out there. I meant to include those. I can pass those along though if whoever is interested.
Great. I'll get you in touch with the questioner. Did you compute the reference trajectory in the CR3BP using FreeFlyer, or how did you get that reference trajectory?
I use MATLAB actually. So a lot of the tools, I'm actually also a PhD student in grad school. So some of the tools I use are in MATLAB and C++. So I was able to pull out those patch points in MATLAB.
You heard me, Brian. I use everything. I use FreeFlyer for everything except turning on the lights.
I got to be honest though.